Okay friends, continuing with the question number 14. Question number 14. When subjected to a unit step input, the closed loop control system shown in the figure will have a steady state error. Okay, so we are subjecting the system to a unit step input, then the closed loop system shown in the figure will have a steady state error. So we will have to calculate the steady state error of the system. So here you can see the input is R of S, our output is Y of S, and then this is a closed loop feedback system with the gains 3 by S and 2 divided by S plus 2. 4 choices are given. This is a 2005 2-mark question. So recreating this figure as a signal flow graph. So we are converting the block diagram to a signal flow graph with all the gains. So the gain is a negative feedback, becomes -1. And then the forward of the transfer functions are 1 and 1, and then it is 3 by S and 2 divided by S plus 2, and the input is R of S and the output is Y of S. So this is the converted signal flow graph of our block diagram. Now we are going to find out the forward path gains. Now the first forward path is P1, which is -1 into 2 divided by S plus 2, which will be in this form. So it is -1 into 2 divided by S plus 2, and it becomes -2 divided by S plus 2. The second forward path is P2, which is 3 by S and 2 divided by S plus 2. So it is 3 by S into 2 divided by S plus 2, which becomes equal to 6 divided by S into S plus 2. Now we are going to find out the individual loop gains. Individual loop gains including the first loop, including 3 divided by S and 2 divided by S plus 2, which will give you -6 divided by S into S plus 2, and loop touches the forward path, therefore delta 1 is equal to 1 and delta 2 is equal to 1. Okay, so now we are going to find out 1 minus L1. Okay, so 1 minus L1. So what is L1? L1 is -6 divided by S into S plus 2. So it is 1 minus of -6. So it becomes 1 plus 6 divided by S into S plus 2, which will give you delta as, so this is delta is equal to 1 minus L1. So it becomes equal to 1 plus 6 divided by S into S plus 2, or it becomes equal to S into S plus 2 plus 6 divided by S into S plus 2. So we have obtained the value of delta, and we have obtained the value of P1 and P2, and now we can use the Mason's gain formula. So substituting it into Mason's gain formula, Y of S divided by R of S equals P1 delta 1 plus P2 delta 2, the whole divided by delta. So P1 is obtained, delta 1 is obtained, P2 is obtained, delta 2 is obtained, and delta is also obtained. So substituting all values into this, you will get Y of S divided by R of S as 6 minus 2S divided by S square plus 2S plus 6. Now we have obtained the transfer function of the given block diagram. What is the question? In the question we will have to find out the steady state error of the system. So now we are moving into finding the steady state error of the system. So from the transfer function that we have obtained, it is given that we are giving a unit step input to the system with the R of S is equal to 1 by S. So here you can see Y of S divided by R of S is equal to 6 minus 2S divided by S square plus 2S plus 6. So that means Y of S is equal to R of S into this. So what is our R of S? Our R of S is 1 by S. Okay. So what is our steady state error? Steady state error is ESS, which is equal to R of S minus Y of S. So we know what is R of S because R of S is 1 by S, and what is Y of S? Y of S is equal to R of S into 6 minus 2S divided by S square plus 2S plus 6. So R of S minus R of S into 6 minus 2S divided by S square plus 2S plus 6. And then you can take R of S as common, and then you can reduce the expression, and when you are reducing the expression you can substitute the value of R of S as 1 by S. So what is our ESS? E of S becomes equal to 1 by S into S square plus 4S divided by S square plus 2S plus 6. Now we will have to use the final value theorem to find the steady state value of the error. So using the final value theorem, what is our ESS? ESS becomes equal to limit s tends to 0 s EFS. So you have the value of EFS and then you will have to find out limit s tends to 0 s EFS, and then our steady state error will become equal to 0. So what is answer for our steady state error? Answer for steady state error is 0. It's a 2-mark question, hence it's a lengthy question, and our answer is option C, 0. So for the given system, our steady state error is equal to 0. So this question is a good question which can be actually split into 2 parts. First, you are going to find out the block diagram transfer function of the system. You are reducing it into signal flow graph, and then you are finding the transfer function, and once you find the transfer function, then you are giving the step input and finding the steady state error of the system. So it's a really lengthy question. It's a 2-mark question. So once you are doing this question can form a stepping block into many other kinds of questions. Okay, so this is a good question, question number 14. Now moving into question number 15. It's a complex type question. The system shown in the figure below can be reduced to the form of this. Okay, so a large block diagram is given, and this large block diagram, they are saying that they are reducing the block diagram into this format. Okay, so you will have to just look into this format, and then the variables are x, y, p and z, and so x, y and z. So choices are given as x is equal to something, y is equal to something, z is equal to something. Then x is equal to 1, y is equal to something, z. Then option C, x is equal to something, y is equal to something, z is equal to 1. In the option D, x is given, y is given, z is given. Again, this is also a 2-mark question. So we will have to reduce the given system into this form, and then you will have to deduce the values of x, y and z. So P will remain the same. So there is no significance for P. So P will always remain the same. In the initial block diagram also, P is given as P itself. Okay. So we will have to reduce this block diagram into this form and find out the values of x, y and z. So the given block diagram is this, and we are going to redraw this block diagram. Redrawing this block diagram by including the summation block. As C0, there is B0, C0, A0. So rearranging the B0, A0, C0 part, because what is our input? Our input is R of S and our output is Y of S. So input is actually going into C0, C1 block. So this is our input R of S. Okay. And this input R of S is going into C0 and C1 blocks. Going into C0, C1 block. So we will have to make this block diagram like into a linear fashion. So it will be more suiting the way that we reduce a block diagram. So this is our R of S, and ultimately this will be our Y of S. So this will be our R of S, and ultimately this will be our Y of S. So we are going to redraw this block diagram into this linear form. Like we will be getting a straight forward gain path. Okay. So converting this block diagram into this form with R of S on the left side and C of S or Y of S on the right side, and we are converting this into its signal flow graph. Okay. So for that we are inserting the nodes like 1, 2, 3, 4, 5 and 6, and keeping the nodes as such, we are going to redraw this diagram. So we are reinserting the nodes 1, 2, 3 is there, 4 is there, 5 is there and 6 is there. So all these are our nodes. So this is the 6th node. So you can convert this block diagram into this signal flow graph. Okay, so you will have to carefully draw down this block diagram, and you have to convert this into this signal flow graph method, into signal flow graph format. Okay, and then we will have to compare this signal flow graph with the already given figure in this question. So here there is only one single feedback path, where the feedback path gain is actually Z. Okay, so we will have to convert this signal flow graph into that format. Okay, so here there are two forward paths. There are two forward paths, P1 and P2. So we are going to make expressions for P1 and P2. The first expression is made for P1 and the second expression is made for P2. And you can see the first forward path includes 1, C0, 1 by S, 1 by S and P. Okay, so the first forward path includes 1, then C0, 1 by S, 1 by S and P, and finally it goes to the output. So this is the straight forward path, that is forward path P1. The second forward path includes 1 C1, 1 by S and P. So it includes 1 C1, 1 by S and P. So this is the second forward path. So this is the first forward path and this is the second forward path. Okay, so we are making expressions for P1 and P2, and then we are making expressions for individual loops. So you will have to find out the loops L1, L2, L3 and L4. L1 includes minus A1 and 1 by S, so it contributes to minus A1 divided by S. L2 includes minus 1 by S, minus 1 by S, minus A0, contributing to A0 divided by S square. L3 includes 1 by S, P and B0, contributing to P B0 divided by S square. And L4 includes B1, P and 1 by S, contributing to B1 P divided by S. So all the loops touch the forward path. So there are no loops which are non-touching with the forward path. So all the individual loops L1, L2, L3 and L4 are touching the forward path. So then delta 1 is equal to 0 and delta 2 is equal to 0. Then we have to find out the value of delta. What is delta? Delta is 1 minus L1 plus L2 plus L3 plus L4. So it becomes equal to 1 plus A0 divided by S square plus A1 divided by S minus B0 P divided by S square minus B1 P divided by S. And using Mason's gain formula, what is our expression? C of S divided by R of S is equal to P1 delta 1 plus P2 delta 2 divided by delta. And this is divided by delta. This is not S, it is P1 delta 1 plus P2 delta 2 divided by delta. So all the values are obtained. You will be able to substitute all the values into the expression, and then you will get C of S divided by R of S as C0 P plus C1 P of S the whole divided by S square plus A0 minus B1 into S plus A0 minus B0 P. And converting this expression into its factorized form, C0 by R of S becomes equal to this format. Okay, here you can see P is there and then the rest of the transfer functions are also there. So it is in the form of X, Y and Z. So from this transfer function we will be able to pick the values of X, Y and Z. And when we are picking the values of X, Y and Z, we will be able to write the expression as XYP divided by 1 minus YZP. So it is XYP divided by 1 minus YZ by P. So comparing these two equations, then you will be getting the value of XY as C0 plus C1 by C1S divided by S square plus A1S plus A0, and YZ is equal to B0 plus B1S divided by S square plus A1S plus A0, and hence we will go with the option D for this question. So what is our option D? Our option D is this. So when you are multiplying the expression, you will be getting the expression exactly similar to YXY as C0 plus C1S divided by S square plus A1S plus A0, and YZ equals B0 plus B1S divided by S square plus A1S plus S0. So for this question we will go with the answer D. Now question number 16. A function y of t satisfies the following equation as dy dt of y of t plus y of t is equal to delta of t, where delta of t is the delta function. Assuming zero initial conditions and denoting the unit step function by u of t, y of t can be of the form is the question. Okay, so these are questions which when you are reading the question you will feel like this question is very difficult to do. Okay, this is a 1 mark question which is a simple question which can be done, and the unit step function is the input and it has to be denoted by u of t, and y of t is to be obtained. So our expression is given as d by dt of y of t plus y of t is equal to delta of t. So taking Laplace transform on both sides, we will get y of s into s plus 1 is equal to 1 because delta of t converts to 1, and then y of s becomes equal to 1 divided by s plus 1. It becomes equal to 1 divided by s plus 1, and when you take the inverse Laplace transform you will get y of t as e raised to minus t u of t, and then what is our answer? Answer D is the option E of minus t u of t. So what is our answer? Y of t is equal to e raised to minus t u of t. So this is a very simple question. But when we are reading the question, it will be a bit confusing and you may feel like it is very difficult to do this question. So you just take the inverse Laplace transform, and taking Laplace transform on both sides, not inverse Laplace transform, taking the Laplace transform on both sides, you will get it as y of s into s plus 1 is equal to 1, where y of s can be written to be 1 divided by s plus 1, and then taking the inverse Laplace transform, y of t becomes equal to e raised to minus t u of t. So option D is answer for this question. Now moving into question number 17. A measurement system shown in the figure uses three subsystems G1, G2 and 1 by G3, whose gains are respectively G1, G2 and 1 by G3. The relative small errors associated with each respective subsystem are epsilon 1, epsilon 2 and epsilon 3 with respect to G1, G2 and G3. Now the error associated with the output is to be found out. So we will have to find out the total error associated with the output when each system is having errors epsilon 1, epsilon 2 and epsilon 3. So dg1 by dg1 equal to epsilon 1, and dg2 by g2 is equal to epsilon 2, and dg3 by g3 is equal to epsilon 3. Okay. So we can see that the total gain is equal to G1, G2 divided by G3. So total gain is equal to G1, G2 divided by G3, and then the output will be equal to G1, G2 by G3 into X. Okay, so where X is the input, because the gains already given are G1, G2 and 1 by G3. So if X is your input, then the total output will be G1, G2 divided by G3 into X. So G1, G2 divided by G3 into X will be the output, where X is the input. Okay. So what will be the ln? Then ln becomes equal to ln y equals ln G1 plus ln G2 minus ln G3 plus ln X. So dy by y equal to dg1 by g1 plus dg2 by g2 minus dg3 by g3 plus dx divided by x. So there is no error specified in the output or in the input. So what is our input? Our input is x, and there is no error specified in the input. So dx divided by x will go to 0. And here dg1 by g1 is equal to epsilon 1, dg2 by g2 is equal to epsilon 2, and dg3 by g3 is equal to epsilon 3. So what is dy by y? Dy by y becomes equal to epsilon 1 plus epsilon 2 minus epsilon 3. So when it is a multiplication of the gain, you will have to take the errors as the sum. So it is a division of the gain, you will have to take the error as the subtractive quantity. So it becomes equal to, this is actually G1, G2 divided by G3. So what will be the corresponding error? So this is the deduction that you can take away from this question. So it will be G1, when it is G1, G2, then it is epsilon 1 plus epsilon 2. When it is G1, G2 divided by G3, then it is epsilon 1 plus epsilon 2 minus epsilon 3. So what is our answer? Our answer is epsilon 1 plus epsilon 2 minus epsilon 3, which is option C for question number 17. Now moving into question number 18. The response h of t of a linear time invariant system to an impulse delta t under initially relaxed condition ht equals e raised to minus t plus e raised to minus 2t. The response of the system to the unit step input is what is the question. Okay, so the response h of t of a linear time invariant system to an impulse delta of t is h of t is equal to e raised to minus t plus e raised to minus 2t. We will have to find out the response of the same system to a unit step input. 4 choices are given. So transfer function of the system is actually the impulse response of the system with 0 initial conditions. So here the initial conditions are 0. So the impulse response is also given as e raised to minus t plus e raised to minus 2t. So the Laplace transform of the e raised to minus t plus e raised to minus 2t will be the transfer function of the system. So what is our transfer function? Our transfer function is obtained as 1 divided by s plus 1 plus 1 divided by s plus 2. So then h of s becomes equal to c of s divided by r of s, and the c of s becomes equal to r of s into 1 divided by s plus 1 plus 1 by s plus 2. And what is r of s given? R of s is 1 by s, which is the step input to the system. So C of S becomes equal to R of S into H of S, or it becomes equal to 1 by S into 1 divided by S plus 1 plus 1 divided by S plus 2. So when you are factorizing this, the expression will become like this. And then what is our C of S? Our C of S is factorized to be 1 by S minus 1 divided by S plus 1 plus 1 by 2 into 1 by S minus 1 divided by S plus 2, which can be written to be 1.5 divided by S minus 1 divided by S plus 1 minus 0.5 divided by S plus 2. So you will have to reduce this expression into this format. Okay. Now to find out the response, you will have to find out the inverse Laplace transform of the given expression. So what is inverse Laplace transform? That is the inverse Laplace transform of 1.5 divided by S minus 1 divided by S plus 1 minus 0.5 divided by S plus 2 will give you C of t as 1.5 e raised to 1.5 into minus e raised to minus t minus 0.5 e raised to minus 2t ut. So this is the net response that we are getting when the system is excited using a step input. So what will be our answer? Our answer will be option C, which is 1.5 e raised to 1.5 into minus e raised to minus t minus 0.5 e raised to minus 2t into u of t. So for question number 18, our answer option will be option C. Moving into question number 19, the transfer function V2 of S divided by V1 of S of the circuit shown below is to be found out. So this is a relatively simple question. We will have to find out the transfer function of V2 of S divided by V1 of S. So it is 100 microfarad, 10 kilo ohm and 100 microfarad capacitance. So across V2 of S we are having 10 kilo ohm resistance and 100 microfarad capacitance. And then there is a series 100 microfarad capacitance also. So we are going to reduce this expression, and then what is our V2 of S divided by V1 of S? V2 of S divided by V1 of S is R. This is R plus C. This is both 100 microfarad. So we will take both of them to be C. So it is R plus 1 divided by CS plus 1 by CS plus R plus 1 by